I'm Nels, and this will be a lecture series mainly going over this book, Categories for the Working Mathematician by Saunders MacLean. I'm an undergraduate, and this is a series to help me work on my mathematical exposition. Uh, I want to also learn more about category theory, and explanations are a way to cement knowledge, and this sounds like fun. So here's some warnings. I am an undergraduate, so I'm not very qualified, and I'm not even close to an expert on the material that we're going over. So there are probably going to be errors in knowledge and understanding and general factual errors. Hopefully not, but that's what comes with inexperience. So before we start to talk about categories, let's talk about diagrams, and more specifically commutative diagrams. A diagram consists of nodes. It's a directed quiver or a directed graph, and it has nodes and it has arrows. In this case, we usually, in the category theoretic context, we usually have our objects being some kind of set or group or ring, and then the arrows between them are, functions or homomorphisms between them. Then, when we want to describe a relationship between sets, so let's say these go between these sets here, or groups or rings, then let's say we want to talk about, we can draw a diagram like this. And then, so C goes here, and G goes here, and F goes here in these directions. So we're also able to talk about their range and domain. Domain and codomain, if you want to be fancy. Why is this called C? I call this H. So now we have a diagram that talks about the relationship between these. So we actually have a function that goes from A to C, but we also have another function that goes to A to C, or morphism, or homomorphism, I mean. So we also have H composed of F, which goes from A to C. So this is another confusion. You can run your finger along this part of the diagram, but the composition is reversed. So it's H of F, even though you run your finger this way. Which is not helpful when you're learning this for the first time, because you look at these and then you can get very bogged down by which direction things go and the way that we write functions normally, where we evaluate them from this direction, but the way that arrows are pointed are in this direction. So that is a mild tangent. This diagram commutes, we say, if you can run, if every path you run through equals each other. So in that case, we mean, does taking this path equal this path? And if we're talking about functions or sets, functions of sets, or homomorphisms between groups or other algebraic properties, algebraic guys will call them. In this case, we would say this commutes if G equals H of F. And we're also talking about every single path between them. So in this case, there are no other interesting paths, but H equals H, F equals F, G equals G. Those are all the paths. We can also have these be squares. So now we're going to have this extend a little bit. Let's get rid of G. So we could say have D. Yes, let's have it go here. Have D, F, we'll call it F prime and H prime. So this would commute if every single path equals each other. So in this case, it's H of F equals H prime of F prime. So that's what makes something commutative. These are really helpful when we're talking about categories, as we'll soon see, because this describes relationships easier than this. Another little extra feature that is useful about commutative diagrams is that we can glue them together. So let's say we have a square like this, A, B, we'll call it A prime and then B prime. And then let's say it's F, F prime, and then we'll just like number these. Let's call them A1, A2. Then let's say we have another commutative diagram, B to B prime, and then again A2, and then we have G and G prime, and C prime, and let's call this A3. If we know that both of these commute, we can smash them together to get this diagram. A, B, C, A prime, B prime, C prime, A1, oops, that's not right. A1, A2, A3. This is G prime, F prime, F, G. So now we had these paths equal each other and these paths equal each other, but now we have much more complicated arguments. We can take this root, and that equals this root, and that equals this root. All roots equal the same because we can just decompose this. So let's say we wanted to show that this root is equal to this root. We can just use the fact that this one is commutative and then take this root, and since these are equal, the G prime part stays the same, and we're good. So we could smash commutative diagrams together to create more complicated structures overall. A category is a collection of objects and a collection of morphisms, and each morphism has a domain and a codomain. What that means is each morphism can be represented like this. So let's say F has a domain A and it has a codomain B. There are multiple ways to write this relationship. So oftentimes, like before with the commutative diagrams, we can write them like this. We can also write them like this. Or, more interestingly, we can say that they're an element of a Hom set or homomorphism set like this. So F is an element of Hom. And this would require that you can actually formulate this as a set itself. So in this case, F is an element of this relationship. All of the morphisms between A and B. All three ways of representing this are all useful in descriptions. This is the best way for commutative diagrams. This is the best way for showing a precise relationship, and this is the best way of showing just an existence relationship. In addition to the elements of a category, its objects and its morphisms/arrows. Just a side note, morphisms and arrows are synonyms. They mean the exact same thing. We have three axioms. We have the closure of composition. So if we have a diagram like this, A, B, C, and then we have F and G, then there exists an arrow between the two. So this goes from A to C, and its name is, remember we go backwards, G of F. And they're equivalent. This diagram commutes. So if we take a path between any two objects, we will also get a morphism between the two. So this exists in our category from A to C. Or we can call it an element in the Hom set of A and C. Then we have an identity morphism. Each object contains an identity morphism. The identity morphism has the domain and codomain to itself. So in this case, our identity morphism is 1A. And it has this property. So let's say we have, we'll call it B. So B to A. And let's say we have C. And let's say we have F. And we have G. So this diagram also commutes. And what I mean by that is if we take this path, it is equivalent to this path. And that would mean that, so we go boom to here, and that would mean that F goes first, and then we have 1A. This is equivalent to if we took the first path. So this is just equivalent to F. So if F goes from B to A, that's too confusing. So if F goes to B to A, so we'll write this like this, a little silly, B to A, and A goes from A to A, then this identity part will just vanish. Same thing happens for G, but in the opposite direction. So we go from A to C, and then this is another path. They commute, so they equal each other, and that will be G of 1A is equivalent to G, since we have both paths, A to C, and then, A to C. Lastly, we also have associativity. And associativity will have, let's say we have a diagram from A to B to C to D, and then let's use F, G, and H. So associativity says that no matter which way we compose it, so let's say we have, since we know this exists, we have G of F, and then we have this here, which is H of G. This diagram commutes. No matter which path you take, they're all going to be equivalent. And that means, so let's take one path. So it'd be H of G of F going in this direction. H of G of F is equal to, let's take this path, H of G of F, which is also equal to this last path, where it is H of G of F. And this is our normal associativity rules. And in the case of functions and homomorphisms, we already know that this holds because of element-wise decomposition of functions. But in category theory, this is a requirement of building a category. Let's first go over some examples. So our first example is going to be a very constructed, arbitrary example. This will be just a category that has 4 objects, and seemingly it looks like it has 3 morphisms, but we're going to go over all the different types of morphisms. So let's just talk about what morphisms exist. So morphisms, we'll say that, so of course by our axioms we have, 1 of A exists in Hom. A to A, and likewise for B, C, and D. So let's go over some more of the interesting ones. So A to B, F exists in that one. And of course, G of F exists in A to C. And then lastly, h of g of f exists in Hom a to d. So these are less obvious forms. We also have g of h goes between these two. And yeah, those are all the composed forms. And then we have, of course, our singletons. So that is a very basic category, but it goes over how composition changes the domain and codomain of these a constructed category. Another example is the example set. Set is a category where all objects are sets and all arrows are the functions between sets. So if we take a little snippet of set, let's say we have the set 1, 2. And so this is an object, and then let's say we want to bring it to the set 3. In this case, we only have one function between the two. And that would be the function that takes everything, that takes 1 to 3 and 2 to 3. Maybe more interestingly is if we have something like, let's say 4 and 5, then we have, so 1 goes to 4. I think we have four different functions. A, B, C, D. So 1 has 2 choices and 2 has 2 choices. So it would be one can go to 4 and 1 can go to 5 and 2, yeah. So that's how we could have 4 different functions between the two. And then for this one, it would be 2 different functions. We'll call this P and Q. Why not? So this is a small snippet of the category of set. We also have something likewise for groups, where it will be group homomorphisms. So let's say we have a group G and H. Then an arrow between them is a group homomorphism. You can see that this is a little different than set because it's a little more restricted. It's only allowed to be the group homomorphisms, not general functions between the group's internal sets. We can also describe some algebraic structures as categories themselves. So we can also describe a group by a category. It is a single object category. Let's say that the object is G. The object doesn't really matter. It's all about the arrows. So let's say G is the 2-element group, where the element A squared is equal to the identity element. Then G has two arrows. Let's call it E and A. So E in this case is the identity element. It goes to itself, and E times A, and A times E is equal to A as well. In this case as well, A squared is equal to E. And you can see how if we can add more elements, and as long as each arrow has an inverse, in this case A itself, then we can call this a group. But it is completely described under category theoretic terms. There are some types of arrows we'd want to go through. There are invertible arrows, and those are such that, let's say we have an arrow, E, from, let's get more marker here, from A to B. This arrow is invertible if there exists some E prime from B to A, such that E times E prime equals E prime E, which equals, no, these do not equal each other, my fault. So E goes from A to A, this will go A to A. So this is 1A, and the opposite sends us to 1B. We say that two objects are isomorphic if there exists an invertible arrow between them. So in this case, A is isomorphic to B, and we will write that either like this, or in some cases we will write this with two dashed arrows. Now we will go over some more interesting arrows. These are monic and epic arrows. Monic arrows are left cancelable. So what that means is a monic arrow, M, from A to B, is monic if for any two arrows, we'll call them F1 and F2, they go from B to C. If F1 of M equals F2 of M implies F1 is equal to F2. So if we see this kind of scenario and M is monic, then the arrows are equal to each other. Epic is the exact opposite. So let's say we have an epic arrow from E from B to C, and we have two arrows G1, G2 from A to B. E of G1. If E of G1 is equal to E of G2, then G1 is equal to G2. In set theory, or in our category set, monic arrows are exactly injective arrows, and epic arrows are exactly surjective arrows. Right and left inverses are exactly what they sound. So let's say we have some H that goes from A to B, then a right inverse is some R from B to A. So yeah, we might as well write it out. Where H of R is equal to 1B. Similarly, for a left inverse, we'll call it W from A to B, and then left inverse from B to A, where L times W is equal to 1A. We will go over three types of objects: initial, terminal, and null. An initial object, let's call it A, is such that for any other object B, there exists exactly one arrow from A to B. So let's say we have an object C. There will be exactly one arrow coming from A to C. The terminal is the exact opposite. Given our previous diagram, we would have exactly one arrow coming from B to A, and likewise from C to A, exactly one. A null object is both. And since it is both, for any arrow, for any two objects, let's say A and the null object N, there must exist exactly one arrow from A to N. If there exist two null objects, we'll call it N prime, then it also has this property. But then, since there must exist an identity element between the two, we'll call it 1n and 1n prime. These arrows, since there can only exist one arrow from n to n prime, and likewise, the composition, let's call these f and g, the composition g of f is an arrow from n to n, but since there can only be exactly one arrow that goes from n to n, g of f must equal 1n. Therefore, g of f is invertible and therefore these are isomorphic. So if you have a null object, it is unique up to isomorphism. So we will go over a meat of categories, and that is functors. Functors send categories to categories. So in other words, we have a functor T that sends the category C to B. It has two types of functions. It has a function that sends objects to objects. So if there's an object in C, our functor T will send that to an object in B. So let's say C is in the object function, is an object of C, which we can denote like this. T of C will send it to the objects of B. Similarly, the arrow function will send arrows in C to arrows in B. They will also preserve the source and destination of those arrows. So, in other terms, let's say F is an arrow in the Hom set C to C prime, e.g. F goes from C to C prime. T of F is an element of the Hom set T of C to T of C prime, or more classically, it is written T of F is from TC to TC prime. So object functions, so functors I mean, will send objects to objects and arrows to arrows and preserve structure. Diagrammatically, also on top of that, we can rewrite this as something like C to C prime F. A functor preserves this by looking like this. And this diagram is in B, while this is in C. So the functor can send them to each other. A functor has two additional properties. If the functor will also send identity elements to identity elements, so T of 1 of B, nope, we are going to call this C. Okay. Functors will also send identity elements to identity elements. So let's say we have object C in C, and it has identity arrow 1C. Our functor will send 1C to 1 of TC. So in this case, TC, 1 of TC, which is equivalent to, it will also preserve composition. So if we have some F composed of G that goes from A to C, T of G is equal to T of F composed of T of G. From our previous example, if we have some diagram like this obviously commutes because of our composition law. A functor preserves that commutative diagram. So for some A, B, and C, if we take the route from A to C, it'll be the same as taking the composed route from A to C. We'll go over an example. This is the power set example. Power set will send sets to set. So as we can remember, the power set will send, let's say, we call it P. Let's say it sends the set 1, 2 to the set, it'll be the empty set, 1, 2, and, the set is in its entirety, 1 and 2. It will send functions from set to equivalent functions that take in subsets and produce its image. So in this case, we will have, let's say we have a function from A to B. Then the power set version of f will send a subset. So a subset of A sent through f will be its image to B. So let's say A prime is a subset of A. Then power function of f of A will be an element of the power set function of B. In this case, this is the exact same thing as asking what the image of a function is of a subset of its domain. Now, we can also tell that the identity stays to the identity as the identity action on a set, the identity function, will send its image to the same exact image, which is the identity of a power set. In other terms, let's say we have a set A. The identity function, I, will also send subsets A prime will just equal A prime. And that is the exact same thing as the identity element, the identity arrow of power set of A. So P of I is what we are expecting. Composition is also the same because images will transform under composed functions identically the same way. Lastly, for this video, we're going to talk about natural transformations. Natural transformations send functors to functors. Diagrammatically, let's say we have two functors. They're going from C to B. Let's call them S and F. And T, I mean. A natural transformation will send S to F. There are two ways that we usually write this. So S gets sent, we put a dot on the top, to T, and we call the natural transformation tau. Or we can write it like this, with two curved arrows. We have S on the top and T on the bottom. And then we have big double arrow here with the natural transformation. Natural transformations send objects to objects composed under the composed under functors, but preserve structure between the two functors. What that means is, given a natural transformation, it gives an arrow for any object in C. So, say a natural transformation, any object in C, a natural transformation gives us an arrow, tau of C. And this is an arrow from S of C to T of C. In other words, tau of C is an element of HOM of B. So this is new notation. This means that we are working under, this is a HOM set under B, which we know is two objects, S of C, T to C. So T of C is just an arrow between C's. They also satisfy this commutative diagram. For any F from C to C prime, the natural transformation preserves this F under both S and T. So we produce those. We compose this under our functors. We have T of C, and then we have T of F, and then, oh, oops, these should be S. We have S of C, then we have S of F, and then S of C prime. And we'll put a semicolon there to note that these are two different things. Then we have T of C, and there's an arrow to T of F, and then we have T of C prime. Our natural transformations complete this commutative diagram. So this will be T of C, and this will be T of C prime. In this case, S of C, if we run our finger through this diagram, is equivalent to this. I'm going to write this down in symbols, and we'll see why we like to usually write this as its commutative diagram, because this implies that T of F composed of tau of C is equal to tau of C prime composed of S of F. This is incredibly nasty and does not really tell you what's going on. It just preserves the structure between two natural transformations. If each of these are also invertible, we call this natural transformation a natural isomorphism. And in that case, the two functors are essentially equivalent. So, to recap, we went over commutative diagrams, we went over categories, we went over types of arrows, we went over functors between categories, and we talked about natural transformations between functors. We might do some more examples on natural transformations in the next episode, if that's created. Otherwise, thank you for watching, and leave a comment below if you have any questions. You probably do, because this is not the greatest video ever, but have a good night.